So for this video, I want to look at application problems using exponents and logarithms. First one here is once again, we have a bacteria growth. When I first introduced this, we looked at a problem like this. But we saw that a bacteria has 360 bacteria after 5 minutes from the start, and then 1,000 bacteria after 20. What's the initial population of the culture? That might be what we're wondering. Well, to find this, we can look at our continuously compounding, in this case, population growth, right? P is the starting amount, A is the amount after time t with growth rate R. We don't know what the starting amount P is. We want to find that. And we don't know what the rate of growth is. We do, however, know what a certain A is. So I'm going to say A5 for t equal to 5 and A20 for t equal to 20. Of course, time in this case is going to be in minutes, so the rate's going to be involved in minutes, not years, as we've talked about in compounding interest. Okay, there's probably a number of ways you can solve this problem, but this is what I'm going to look at. Let's create two different equations out of this. First off, let's plug in A5 and T5. So A5 is going to be 360 equals PE to the R times 5, right? 5 was the time. The other equation we get is the exact same one, but now plug in A20 here. So this was A5. This is A20. So 1,000 equals PE to the R times 20. So to solve it, let's solve for P for this one. Right? P equals this. Now I can plug that into this one here. So we get 360 equals 1,000 R times 20 times E to the R 5, or I should say 5R and 20R here. Okay, I can move things around a little bit, make my life a little bit easier to work with. I'm going to divide out the 1,000 from this side. That's going to give me 0.360. And on this side, I have e to the 5r over e to the 20r. Well, this is dividing of like bases, e in this case. I can do that by subtracting the exponents. But those are like terms, so I can make that into negative 15r. And now we just have a simple exponential equation. I can solve this by taking the natural log of both sides. And then dividing by negative 15. So our rate is going to be approximately, I should say, 0.0681. And we want to figure out what's the initial population of our culture. Well, once again, we have this situation. So we have A equals PE to the RT. And I can plug in my knowns now. I know A5. I can do A5 or A20. It doesn't matter. And the T was 5 minutes. And we know the rate. The rate is 0.0681 times 5. The only unknown here is P. So we can find that by dividing out this number. And doing that, we're going to get P equal to, rounded to the nearest whole number is 256. So that's our initial population is 256. A exponential equation that represents the situation is going to be A equal to 256 e to the, let me get rid of this, R times t. This models the situation nicely. Now, to the nearest minute, how long does it take for the population to double? So let's start off with this model here. We start off with 256. So what we want to do is we want to double it. Well, double 256 is 512. And we're asking, what is the time it takes? Well, we can divide by 256 and then take the natural log of both sides. That's going to get rid of that e there. So we have the natural log. 512 divided by 256 is 2. 0.0681 t. Divide that out. And we're going to get t approximately equal to 10.18. And in the beginning, we said that everything was in minutes, right? And to the nearest minute, that would be 10 minutes. So it takes about 10 minutes to double this population. If we look here, after 20 minutes, right, it should have doubled twice. And if we start off with 256, 256 times 2 is 512, times 2 is 1024. And that is just about 1,000. The reason why it's off is because we've been using approximations, right? We did an approximate of the rate, which gave us, an approximation of the beginning population, and that's what made it, go off. But that seems about reasonable to what our situation is. Okay, for the next one, we have this interesting function here. This is actually similar to what's called a sigmoid function, classic function to use in a lot of situations. But this thing models how many people have heard a rumor in a certain town after t days. So how many people started the rumor is the exact same idea as t equal to 0. If you plug t equal to 0 into here, we get a negative 0.7 times 0, so we get just 0. But e to the 0 is just 1, so that just becomes 1 here. So that's going to be 49. 1 plus 49 is 50, and that gives us 10. And as you can see on the graph, if we graph that thing, 0 does go to 10. Okay, now after 3 days, so the same idea, we're going to do 500 over 1 plus 49 e to the negative 0.7 times 3. T is in days, so we can just plug 3 into there. And all we're going to do is simplify this statement down. Really, just plug it into a calculator. 500 divided by 1 plus 49 e to the power of negative 0.7 times 3. I'm getting 71.4, but of course you can't have 0.4 per person. This is just equal to 71. Looking on the graph, we have 3 days here. It's somewhere around here. Yeah, 71.425, which is what I got. Okay, finally, as t increases without bound, so as t goes to infinity, what value does n approach? Now, we can, of course, look at the graph, but I want to first look at the equation. This is our equation here. Now, as n goes off to infinity, so this gets bigger and bigger and bigger and bigger. What we really are looking at is what happens to e to the power of, well, as these numbers get bigger and bigger, right, that's going to be t equal to 1,000, 1 million, 1 billion. Negative 0.7 is going to make that a very large negative number, right? Negative 0.7 times, 100 is, negative 70. Negative 0.7 times 1,000 is negative 700. It just gets bigger and bigger, but in a negative direction. So the question is, what happens when e to the power of negative, let me do it like this, turn that off for a moment. All I've written here is e to the power of negative x. And as you can see on the graph here, it goes down, and it goes down to 0. It'll never cross this line, but it'll go closer and closer to 0. So the whole point is that as t goes off to infinity, this portion here, this e to the power of that, this just goes to 0. That means we have 500 over 1 plus 49 times 0, which is 500 over 1, which is 500. Now, what does that mean? That means probably there's only 500 people living in this town. So let's re-look at the other equation. So this is back to our original graph. And you can see that this thing gets closer and closer. If I draw on there, it's getting closer and closer to 500. It never actually gets there. It'll say it does because Desmos is estimating it there, but it'll never go above that value. And it gets pretty close after pretty much 15 days. So that's by the time it really spreads pretty much the entire population. Okay, half-life is how long a radioactive material takes to decay. It's a half of the amount that it is. That's why it's called a half-life. However long it takes to decay, half as much. Because radioactive material, parts of it comes off as radiation, which is energy, so it has to come from somewhere, and that's coming from the radioactive material. It's actually shooting off of that material. Anyways, we can look at continuously. In this case, it's kind of like a population. It's continuously decaying here, and we're looking for when is it half of the original amount. Well, let's plug this in. A is just 1/2 p. I can divide out the p. That gives me 1/2 e to the RT. Take the natural log of both sides. That gives me the natural log of 1/2 equals RT. And typically we'll write this as natural log of 2 to the negative 1. And I can move this negative on the outside. So we get the negative natural log of 2 equals R times T. This is the half-life formula. We can either solve for R if we want or T if we want, depending on what we're looking for. And we don't need to know, this is the important thing, we don't need to know how much we started with. All that matters is how fast the material decays. That's what the rate is saying here. Or if we know how long it takes to decay to half the amount, then we can plug it in for T and find the rate of decay. Okay, say we have 250 grams of some radioactive substance. So this is kind of like our starting amount. After 250 minutes, the sample has decayed to 32 grams. We want to write an exponential model, that models the situation. So we need to know what is the what is the rate of growth and the starting amount. Well, we have the starting amount. All we have to find now is the rate of growth. So we know that A after 250 minutes is 32. So we have 32, right? This is A equals P E the RT. The starting amount was 250. We do not know the rate, but we know the time. The time was 250 minutes. Now we can solve for R. I'm going to take a natural log of both sides again. So we're going to get 32 over 250. The natural log of that equals R times 250. I can just divide by 250 here. So our rate is going to be, let me calculate that out. I'm getting negative 0.0082. And it's important to note this is negative, and that's what you expect because this is a decaying situation, right? It's radioactive, it's decaying, how much is there. So the model is going to be the initial amount is 250, the rate is 0.082 times by that time. That's the model for this situation. Now, to the nearest minute, what is the half-life of the substance? Well, all we have to know is the rate of time. So this is going to be the time for the half-life. So the time for the half-life is going to be the negative natural log of 2 divided by the rate. And our rate is negative 0.0082. Plugging that into a calculator, of course the negatives cancel. We get 84.53. This is a time. Time is in minutes here. So we get minutes. And let's see, 84 let's say it's about 85 minutes, right? If we do 85 times 3, this gives us 255. This is just about the 250 minutes. So if we cut this in half and then half again and then half one more time, we should be just around 32 because it decayed it to half-life 3 times. So cut in half, 125, cut in half again. That's going to give us 62.5. And then we're going to cut in half one more time. So divided by 2 one more time. And that's going to give us 31.25. So after three divisions, 3 half-lives, we get about 31.25, which is just about 32 grams. So all I'm doing there is I'm just checking my work to making sure my answer is correct. So this 84.53 is the half-life, how long it takes for it to decay half as much. It doesn't matter how much started with. If it was 250, then it'll go down to 125 after 85 minutes. If it was 2, it'll go down to 1 after 85 minutes. If it was 1,000, it'll go down to 500 after 85 minutes. It's always half the amount. Now, the half-life of erbium-165, this is an isotope of erbium, is 10.4 hours. What is the hourly decay rate? And the important thing to note here is that there is no constant hourly decay rate because this is not a linear growth. Linear growth has an hourly decay rate that you would kind of expect as a number. Here, we don't have an hourly decay rate as a number, but as a percentage. The percentage is lost over a certain amount, not a flat rate. To find that, all we have to really do is look at the half-life, right? 10.4. That means that negative ln 2 equals r times t, right? We know the time for the half-life. This is the half-life time. That's just 10.4 hours. So we can find the rate. That's going to give us, let's calculate that. Going to give us just about negative 0.067. So to find the hourly decay rate, it doesn't matter what starting amount we have because every single hour it's going to decay by the same percentage. Not the same number, but the same percentage. So I'm going to start off with let's just say we have 100 grams of erbium-165. So the amount that we're going to have after it decays, after 1 hour with the current rate that it decays, right, times by 1 hour here for R, we can plug that in. You're going to see we get, we get 93.52. So the actual decay rate is going to be a percentage, right? We had 100 and then it decayed to 93.52. I can write that as 93.52 divided by 100 equals 0.9352, and this becomes a percentage, 93.52%. That's actually why I chose 100, is because it translates nicely into the percentage. So after an hour, 93.52% of the material is left. So just about 6.5% of it has decayed. And let's test this, right? Let's test this with a different amount, right? Let's test it with like 80. If we started off with 80 grams, after 1 hour, we should expect there to only be, I'm going to multiply this by the percentage 93.52. So if I do that, I get 80 times 0.9352. I expect there to be just about 74.82 grams left. And if I plug this into our formula, if I plug in 80 after 1 hour with this current decay rate, plugging in E to that number there, I get 74.8156, which is 74.82. So that's correct. I've got the right decay rate. So this is the hourly decay rate. Really what we're saying is it's decaying off 100% minus. That's going to give us we're removing every single hour 6.48%. So either way you want to think about it, we have 93.52% left, or 6.48% is being removed. It's both the same thing. That's kind of the process to find it. All right, give it a try in numbers 13, 14, and 15.